Hello, everyone. Welcome to part three. This is a four-part lecture on chemistry. We're going to jump into the section on water now and talk about that. Um, Water is very important. I'm going to say we're roughly two-thirds water, so we're roughly about 75%. I mean, that number is, of course, usually given in a range, so that's okay. But I'm going to say we're roughly two-thirds water. So water is very important to understand when it comes to the body. There's a few things, some of the properties of water that are discussed really exist mostly because of hydrogen bonds. The hydrogen bonds exist there. So solubility, water is a great solvent. We call it the universal solvent because so many things dissolve in it. It dissolves a great number of things. It dissolves anything that has a charge that's polar or ionic compounds. It's a lot of chemical reactions happen in it. So there is a high amount of reactivity. Chemical reactions in our body, they occur in water. For example, dehydration, hydrolysis reactions, for example. High heat capacity. Water can absorb a lot of heat before it actually changes state due to the presence of hydrogen bonds. So it stays liquids over a wide range of temperatures. Takes a lot of heat to make it turn to a gas. And then when it actually converts to a gas, it takes heat with it. So that allows us to evaporate water off the body and as we sweat to cool the body off. So that's what happens when we sweat. Why sweating cools our body to regulate the body heat. And it also reduces friction, acts as a good lubricant as well. So as we talk about that, that'll be some things we'll talk about later. Now, one of the things I want to define and really discuss is the idea that water is got good solubility. It forms solutions. What is a solution? A solution is what we call homogeneous. What do we mean by homogeneous? Homogeneous means that it is the same throughout. It is a mixture where a solvent is placed in a solute. A solute is placed in a solvent, I meant to say. The solute is what gets dissolved, and the solvent is what does the dissolving. And that's the thing that dissolves stuff. So, for example, one of these things we might talk about is if we have a solution, we use large organic molecules. That's basically colloid. If we have particles that are too large or hydrophobic, so they stay in solution. To stay in. They're too big to stay in solution, or they're hydrophobic. They settle out because of gravity. I think that I need to retweak that phrasing there. It's just really not the best phrasing that I've ever written. And solutions are measured by how concentrated they are. And what I mean by that is think about like sweet tea versus sweetened iced tea. Good example of that. Okay, so one of the things I want to talk about what water does is when you have aqueous solutions is that things do what we call dissociation. Water is polar. So it has a positive end, it has a negative end. So the positive end is where the hydrogen atoms are, the negative end where the oxygen is. So it's polar. So if we take a look at a water molecule and we remember that in water molecules we have this oxygen here and that it is partially negative. And we have the two hydrogens, okay? And they are partially positive. We say this is a polar compound. Now, what will happen is, if I took something like NaCl and I added this to water, and I put water, what's going to happen is it's going to form up into its ions, Na plus and Cl minus. Okay, these ions will form. Now, what's going to happen with these ions is Na plus is going to get attracted to the negative end because opposites attract, and Cl minus is going to get attracted to the positive end. And what's going to happen is water molecules, other waters, are going to come in and surround it, okay? Other water molecules are going to come around here and they're going to surround this, okay? They're going to find these ions and they're going to surround them. Other water molecules will. And what we refer to this is a hydration sphere, okay, we will form what is called a hydration sphere, where water molecules surround these ions. And basically what they're going to do is if we let it, sodium cation and chloride anion would form ionic bond with each other. But what we've done by placing them in water is the water molecules not only split it in half, but keeps it apart. It keeps it separate. And this allows it to stay. This is a process right here called ionization or dissociation. It dissociates. Water dissociates it. Compound that is polar or ionic is placed in water and it splits. Okay. Especially ionic compounds. Now, when ionic compounds split into their ions, this is what we call ionization. It ionizes, it dissociates or ionizes. Aqueous solutions can contain cations and they can contain anions. Okay. Now, water is positive. What it will do is surround the positive ends surround the anions, the negative ends surround the cations, and this results in a hydration sphere. And basically, this isolates the ions from each other, preventing the formation of ionic bonds. Okay, so this keeps these things apart. Now, that's very important that we learn that. So that's what a hydration sphere. This can happen in polar compounds, or this can happen in ionic compounds. Okay. So we can have electrolytes, and these electrolytes, when these things ionize, when they dissociate or ionize, they're ions, they will have electricity. An electrolyte is a soluble molecule whose ions carry charges, okay? Like sodium chloride is an electrolyte because what it will do is it will ionize. Potassium chloride, calcium phosphate, sodium bicarbonate, magnesium chloride, sodium hydrogen phosphate, sodium sulfate. These are all electrolytes because they are molecules that are ionic who will dissociate into ions, okay? All right. Now, water is polar. Water and big white bears are both polar, okay? And since water is a polar compound, that means that it will help me dissolve things that have charges to them, okay? Now, if we have something that is water-fearing, then it does not interact with water, so that means it cannot have a charge. So hydrophobic substances, any molecules that fear water, they're molecules without a charge. These will be non-water soluble. These are things that are non-polar covalent bonds that form them as non-polar covalent bonds. Hydrophilic, on the other hand, is anything that likes water. We say hydro. So remember, hydro meaning water, phobos meaning fear, philos meaning loving. These are water-loving. They are soluble in water, okay? They actually dissolve in water and they will like water. They will interact with water. They love it. They like it. They want to be around it. This compound will have a charge, so it will dissolve in water because it would be a polar molecule or compound. Now, in hydrophobic substances, we also refer to it as being lipophilic because it's lipid-loving. And if it is hydrophilic, we call it lipophobic because it's lipid-fearing. So if you like water, then you don't like lipids. And if you don't like water, then you will like lipids, okay? All right, now here's something very big to talk about, is this idea that water is not just H2O. It is an equilibrium between two ions. Now, I'm going to talk about hydronium as H+. Now, I know a lot of people get really aggravated with me on that. There's some chemistry people out there that get a little aggravated that I use H+, and I'm not using something else. But H+ and OH-. H+ is hydronium. There should be a superscript there. I need to add superscripts to these. I never did. I kind of missed it when I wrote it. But these guys, hydronium ions, OH- hydroxide ions. And what we do is we take these guys and we measure the amount of hydrogen ion concentration. What is the hydrogen ion concentration? We measure that in moles per liter, and we use that to measure that moles per liter of hydrogen ions. We use what's called the pH scale. Now, to calculate pH, we need a formula. Is hydrogen ions calculate hydrogen ion concentration from the pH? We need that hydrogen ion concentration is equal to 10 to the negative pH, or 1 times 10 to the negative pH. So we could say it a few different ways. We could say that hydrogen ion concentration is 1 times 10 to the negative pH, or just to say 10 to the negative pH, okay? So, for example, if I had a substance out here, let's say I had a pH that was 1, okay? Then this means the hydrogen ion concentration is equal to 10 to the negative 1. Now, how do we do that? What we do is we will take 1.0, okay? And we're going to always take it as 1.0. And what we're going to do is we're going to take this decimal point and move it one place to the left. And it's going to be 0.1 moles per liter, okay? And if we had a pH that was 2, then the hydrogen ion concentration is 10 to the negative 2. We have 1.0. What we're going to do is we're going to take this decimal, 1, 2. So, of course, we can just say 0.01 moles per liter, okay? So we'll say 0.01 moles per liter. And if we had let's say we have a pH that equals 6, okay? Then the hydrogen ion concentration is 10 to the negative 6. So we take 1.0. We move the decimal to the left 6 places, okay? 1, 2, 3, 4, 5, 6. And it'd be 1, 2, 3. I'm missing one. There we go. Okay, so that gives us just a few samples of that, okay, that we can do it. So basically all you're doing here is you're moving that decimal that many times, okay? So I gave some examples. So I will expect you to be able to do this on a test. I will have you calculate that. All you're doing is taking 1.0 and moving the decimal to the left that many times for the pH, okay? Moles per liter, okay? And I will expect you to be able to do that for the test. It will be a test question. Okay. Now, anything that has a pH that is 7, we say it's neutral. And if it has a pH less than 7, we say that it's acidic. And if it has a pH greater than 7, we say that it is basic. Now, anything that is neutral, H pluses always equal OH minuses. Anything that is acidic, H pluses are greater than OH minuses. And anything that is basic, H plus is less than OH minus. Now, we say that anything acidic increases H plus concentration, and anything that is basic decreases H plus concentration. So if you're acidic, we call you a proton donor because H plus is essentially a proton. And if you are basic, we call you a proton acceptor because H plus basically a proton, you decrease it, you accept it. So here's a great example. HCl will dissociate into H plus and Cl minus. And this should also be HCl lowercase l. I apologize. It wants to change things on me automatically. It doesn't do chemical formulas very well in PowerPoint. Sometimes it wants to automatically change it for me, and I apologize, but that was driving me crazy. I apologize. I had to do that. Anyway, okay. And here we have like the ammonia, NH3. We add a hydrogen ion to it, make NH4 plus, ammonium ion. Okay. All right. Now, one of these things this might show you here is the relationship between pH and hydrogen ion concentration is an inverse one. 0.1 is far larger than 0.000 0.00001 moles per liter. Okay, so anytime the hydrogen ion concentration goes up, we actually reduce the pH. And anytime the hydrogen ion concentration goes down, the pH goes up. That relationship is very important to know. We must understand that. Very big deal these statements are, okay? Very big deal to understand. Sorry, my dogs keep coming up wanting petting. They're distracting me a lot. I'm trying my best to focus here, and they just keep coming up. Okay. So this is your pH scale. Don't have to memorize this, but right here you can see 10 to the negative pH. Hydrogen ions is 10 to the negative pH. The pH of 1, 10 to the negative 1. Okay. Here you can see that 1 mole of hydrochloric acid would have a pH of 0. That should be 100% hydrogen ions. Okay, so, all right. So very acidic, very basic, neutral, pH is 7. Okay. All right, now human blood is got a pH of 7.35, 7.45, so it is slightly basic. Anything that is below 7.35, we call this acidosis. Anything above 7.45, we call this alkalosis. You better know the pH range of the body. That pH range of your blood is a very important value to know. Basically, if it comes out of my mouth, it usually is on tests. Most of the time, if I talk about it, it's going to be on the test somewhere. Usually, tests or quizzes or something. Now, anytime you ever increase hydrogen ions, they can damage your proteins, they can damage your tissues, so we have to highly regulate it. So one of the ways we do this is with buffer systems. One of the things I kind of like to explain, let's say that I took some acid, like I had a drop of acid, and I put this acid into a beaker that contained water. The pH would go up pretty dramatically. But if I put the same amount of acid, 1 drop of acid, in a beaker of blood, the pH wouldn't change very much. It'd be negligible if it did change. Why is that? Blood has buffers in it, and what buffers do is they prevent changes to the pH balance of the body. They prevent these dramatic changes. Now, they prevent dramatic changes. They can get overwhelmed, and that's what happens in acidosis alkalosis, is your buffer systems get overwhelmed. Okay. Now, what is a salt? A salt is formed when I take something like, let's say I take hydrochloric acid and sodium hydroxide, and I make NaCl. The salt is formed when an acid base reacts. A salt is an ionic compound containing any cation except H plus and OH minus. Okay, they're formed by ionic bonds when we dissociate acids, and acids and bases react. Okay. They form, when the acids and bases react, when sodium hydroxide and hydrochloric acid react, they form sodium chloride. And this can affect, some can actually affect, can actually act as a weak acid or weak base. Sometimes they can actually affect pHs of systems when we add them. So they can actually, some of these salts actually are known to act as weak acids, weak bases. Part of this has to do with a different definition of acids and bases. We're using Arrhenius acids and bases. You can look at Lewis acids and bases and things like that. If you ever had good chemistry courses, you learned about Bronsted-Lowry acids and bases. You learned about Lewis acids and bases. We pretty much use Arrhenius acids and bases definition. We use Arrhenius. Now, buffers, they stabilize this. Buffers' job is to stabilize the pH of a solution by either removing or adding back, replacing H pluses. They have a weak acid, weak base combination, and they help maintain body fluid pH. So what they'll basically do is a buffer system can add hydrogen ions when we get too basic, and they can pick up hydrogen ions when they get too acidic. They can act as a proton donor or proton acceptor. The buffer systems. We'll learn buffer systems in A&P2, but buffer system, this is very important for future down the line A&P2 stuff, okay? Okay, so this concludes that section, and I'm going to stop here, and I'm going to do a whole section just on organic chemistry. Okay.